Let's start here with the parallelograms. And, well, I'm going to put these marks on it. A parallelogram is a quadrilateral with two pairs of opposite sides parallel. That's the very definition. Now our first theorem, 8.3, is going to tell us that the opposite sides are congruent as well. Now we're going to prove this in a little bit after we see our next theorem, but I just want you to know this. You can memorize it if you like, and just if you're looking ahead, the converse of this, that's next section, is also true. Now the next theorem, or property of a parallelogram, if you will, is that the opposite angles are congruent. So I'm starting here. I've got this figure, PQRS, again marked as a parallelogram. Let me color in those angles. The red angles are congruent, as are the blue. Let's have a look here, just so you know, next chapter or next section, you'll see the converse is also true. Now let's go back, and we're going to prove 8.3 and 8.4. I'm going to start with this, a parallelogram. By the very definition, I've got a quadrilateral with two pairs of opposite sides parallel. This time, I'm going to cut them with a transversal, little Tommy transversal. Why? Well, any 2 points determine a unique line, ray, or segment. And from that, I'm going to say this red line is now a transversal. Angles 1 and 2, acting on these parallel lines, form or are alternate interior angles, and therefore they are congruent. And 3 and 4, same argument. Given these this pair of parallel lines, same transversal, the two red angles are congruent as well. All I need now is this side. PR is congruent to itself by the reflexive property, and therefore I've got a pair of congruent triangles by angle, side, angle. Well, here's the two triangles in question. This one, and ready, whoa, it's rotation, right? So this one and its rotation. Those two triangles are congruent. Well, I got two triangles congruent, then I've got corresponding parts of congruent triangles, says their corresponding sides are congruent. And right there, that's going to take care of theorem 8.3. And how about 8.4? Well, these two angles are, again, corresponding parts of congruent triangles, so they are congruent. That takes care of theorem 8.4. I suppose to prove this theorem, we'd have to draw the diagonal QS and repeat the procedure to get the other two angles, but you get the idea. Here we're going to have a look at theorem 8.5, which tells us that if this figure is a parallelogram, then its consecutive interior angles are supplementary. That is X and Y, or the red and blue. Now this is really just theorem 3.3, way back when. Remember, I've got parallel lines here. Right here I've got the blue and the purple cut by this red transversal, and that makes the two consecutive interior angles supplementary. Easy as that. So we could look at X and Y, or those two angles at P and Q, or we could say over here we've got a red and a green as well. The purple can be our transversal, and so can the blue. And our final theorem for this section, 8.6, tells us that with this parallelogram, I can draw these two diagonals. I'll color them red and blue respectively. They meet at a point called M, and that M is the midpoint of both diagonals. Well, that's what it means to say that diagonals bisect each other. And I want to show you one interesting thing here. Let's just take a circle like that and a circle like that. That may help you see the relationship then. Of course, these two red radii are congruent. The two blue radii are congruent. When the two circles become one, then I have a rectangle. Hey, that's pretty neat. Now let's go back, and we're going to prove this theorem. Starting with opposite sides parallel and congruent, let's first draw the diagonals. They're going to meet at a point I'm going to call M. Well, now we can also look at these as transversals. let's make use of our Theorem 3.1. After all, these parallel lines cut by this transversal means that angles 1 and 2 are alternate interior angles. The parallel lines mean that angles 1 and 2 are congruent. Well, the same thing can be said for angles 3 and 4, and this is the shorthand we used back in Chapter 3. Then I guess we can just, well, see, we could do this. We've got two triangles congruent, angle, side, angle. If you want to see this, they are rotations of each other. Well, since these triangles are congruent, I know that all their corresponding parts are congruent, and therefore we have it. The two red segments are congruent. The two blue right there, the two blue segments are congruent, and we have diagonals that bisect each other. That makes M a midpoint of both.